Oke, saya Hanafi. Saat ini kita sedang menyaksikan International Post Conference yang di antara kerjasama Jepang dan ITB. Ini kita akan
We cannot hear you. We cannot hear you.
Perhatikan, kita akan
Please
dengarkan.
get the device again
Kita akan
and
memulainya.
please restart the presentation.
I'm really sorry.
Kebetulan saat ini saya sudah tampil di urutan
I
kedua.
checked
Ini
my
adalah peserta yang ketiga.
setting, so please give me some minutes.
Okay, this is the first presentation. I am Hanafi. Was
Can
presented
you hear my
in
voice? Can you hear my voice?
number
And
two.
can you?
Okay, let us
see
we
my slide?
see together.
Yes, we can hear you and we can see your slide.
Thank you. Okay. I'm so sorry about my mistake, and I restart my presentation. Hello. My name is Akihiko Nagashima from the University of Electrocommunications. I'd like to talk about a study on multivariate CLA complementing missing time series data. The cortical learning algorithm, CLA, is one of the time series data prediction methods designed based on the human neural cortex. CLA has been reported to be more accurate than LSTM in predicting the time series of taxi rides. In this study, we focus on the case of the input data is missed in the CLA. CLA is inputted the value of time step t, and output the prediction for time step t plus 1. However, the missing values are inputted. CLA is hard to predict next time step. When the input data temporarily miss, CLA may maintain the prediction by inputting the prediction data instead of the real input data. However, the input data continuously miss. CLA cannot maintain the prediction since the prediction errors are accumulated. In this work, we propose a multivariate CLA complementing the missing input data by using different other input data. In multivariate CLA, when one time series data is missing and cannot be predicted, it complements the information from other time series data to enable prediction. Let me explain the conventional CLA. A CLA consists of cells, columns, region, synapses, and input data bits. First, the CLA represents input data at each time step by a combination of active columns. Each column has synapses for several bits, and the column with the most connected bits at 1 is chosen as active column. This process is called spatial pooling. Next, the CLA performs temporal pooling. First, for temporal pooling, CLA activates a cell from the activated columns. When a cell becomes active, for preserving the context, synapses are generated between the cell and the one that was active at the previous time step. The cells connected to the active cell by synapses become predictive. CLA predicts the next time step from the combination of predictive cells. When a column with a predictive cell is active, the predictive cell becomes active. The activation of predictive cell means that the prediction was correct. Next, I describe the learning flow of the proposed multivariate CLA. Multivariate CLA is composed by combining multiple subregions, respectively learning different input data. Spatial pooling are performed in each subregion. Temporal pooling is performed by all subregions synchronously. As a result, cell synapses are also arranged between cells in different subregions. This constructs an intersection synapse network predicting each input data by using other input data. Since each subregion learns different time series data, it may be better not to use information from other subregions. So, to determine which subregion contributes to the prediction of a cell, we introduce a contribution to each synapse. contribution is incremented when the synapse contributes to making a cell predictive, and the cell becomes active in the next time step. When a cell is activated, the proposed multivariate CLA estimates relations among subregions by using the contribution rates. The contribution rates are calculated as the average of the contributions of synapses to each subregions in the cell. The high contribution rate means that the subregion can be utilized in the prediction of the cell. Subregion that is not used for prediction can interfere with prediction. Therefore, the proposed multivariate CLA stops the generation of new intersection synapses to the subregion. For example, in this figure, the contribution rate C3 of subregion 3 is less than alpha per number of data. The proposed multivariate CLA stops generation synapse that connects from subregion 1 to subregion 3. The stop of synapse generation leads to a decrease in the number of intersection synapses to the subregions that are not used for prediction. In contrast, the proposed multivariate CLA retains more synapses for subregions that can be used for prediction. This process is performed in all cells, so that each cell has more synapses only in the subregion used for prediction. If there are missing values in time series data, the proposed multivariate CLA selects predictive cells by using intersection synapses from other subregions. To verify the effectiveness of the proposed method, we use three artificial time series data: sine wave, sawtooth wave, and logistic mapping. Sine wave and sawtooth wave have same period. In contrast, the logistic mapping is periodless. We ran the experiment on four test cases A to D. Case A receives data only in the subregion 1. Cases B and C receives data in the subregion 1 and 2. The case D receives data in all subregions 1, 2, and 3. The learning process stops at the time step t equals 10,000. The input data to the subregion 1 stops at the time step t equals 10,500, and compare RMC in region 1 before and after 500 time steps from t equals 10,500. For example, this figure is a graph of inputs around time step 10,500 of case D. The results of the experiments show that the RMC for each case is shown in the table. The increase in RMC is about 1% when different data of the same period are inputted. From here, I'm going to talk about case D. This figure shows input data and the prediction value on the subregion 1 before and after data missing. X-axis represents time steps, and Y-axis represents the input value. The black dashed line represents the predicted value of the subregion 1. This graph shows that the proposed multivariate CLA is predictable with no missing inputs. Furthermore, this graph shows the predictions for the missing inputs. We see the proposed multivariate CLA can predict the sine wave, even after the input is missing. These are the contribution rate and number of synapses for subregion 1. The x-axis represents time step. The y-axis in the left panel shows the contribution rate, and the y-axis in the right panel shows the number of synapses. The left figure shows that the contribution rate of subregion 2 is higher, while that of subregion 3 is lower. As a result, the number of synapses to subregion 3 decrease. To summarize this study, to maintain the time series data prediction, even when the input data are continuously missing, we proposed a multivariate CLA. As a result of the experiment, proposed methods can complete prediction if there is related data. Thank you for your attention.
Thank you very much for the presentation.